Today, let's design an online payment processing system. Imagine a customer pays $120 for order 84. Our processor captures the charge, but its response disappears. The merchant sees a timeout and retries. Should the customer be charged again? Never. One logical payment must produce at most one captured charge, even when requests, responses, and callbacks are duplicated or delayed. We will follow the same order through the whole design. The goal is not to make failure disappear. The goal is to make every uncertain outcome recoverable. This is an illustrative interview design, not OpenAI's production architecture. Start with a payment intent, not a direct charge. The merchant creates payment intent 84 with an immutable order reference, amount, and currency. The API also receives a merchant-scoped idempotency key. If the create request is retried with the same payload, the system returns the same intent. If that key comes back with a different amount, the request conflicts before any processor call. The intent moves through a small state machine, requires payment method, processing, captured, declined, canceled, or unresolved. Only the payment service may change that authoritative state. At our assumed peak, intent creation reaches 10,000 requests per second. Durable creation should finish within 300 milliseconds at the 95th percentile, so this first write cannot depend on a slow external processor. Confirming a payment creates a durable processor operation. Call it operation 91. The payment intent answers, what does the merchant want? The operation answers, what did we ask one processor to do? It stores the provider, a stable provider request ID, attempt status, timestamps, and the raw outcome reference. Before any network call, one database transaction validates the intent, claims the confirm idempotency key, creates operation 91, marks the intent processing, and writes an outbox event. Then a worker sends the processor request using the same provider request ID on every retry. That order matters. If the worker crashes before the call, another worker resumes the recorded operation. If it crashes after the call, recovery still knows exactly which provider request to query. We never invent a second logical attempt just because one process disappeared. Now the processor captures $120, but the response times out. The worst mistake is to mark the payment failed and immediately start a new charge. A timeout tells us nothing about whether the remote side committed, so operation 91 becomes unknown. The intent becomes unresolved, and the merchant receives a pending response with the existing payment ID. A reconciler queries the processor using the stable request reference. An authenticated callback may arrive first. Either path enters the same inbox, deduplicates the provider event, and tries one guarded state transition. If the processor confirms capture, one local transaction marks operation 91 succeeded, moves the intent to captured, appends balanced financial journal entries, and writes a merchant notification outbox event. If the processor confirms decline, it records decline instead. If the provider remains unreachable, the system stays unresolved and keeps reconciling with bounded backoff. Unknown is a real state. It is safer than pretending certainty. A callback and a reconciliation query can report the same capture at the same time. Both carry the provider operation identity. A unique inbox key makes duplicate delivery harmless. Then, a compare and set transition allows captured only from an eligible earlier state. The winner writes the financial event. The loser reads the already completed result and stops. Late events are checked against the state machine. A delayed processing callback cannot move a captured payment backward. A repeated captured callback cannot append the journal twice. And every rejected transition is recorded for investigation rather than silently discarded. The processor is authoritative about what happened on its network. Our payment database is authoritative about what the merchant sees. Reconciliation is the bridge between those two truths. After capture, the merchant can request full or partial refunds. Suppose two operators each request an $80 refund against the same $120 payment. Each request looks valid alone, but together they exceed the capture. Inside one transaction, the refund service locks or version checks the payment's refund aggregate, computes completed plus reserved refund amount, and reserves capacity for only the request that still fits. The second request receives a conflict. Each accepted refund gets its own idempotency record and stable processor operation, so timeouts follow the same unknown and reconcile path as capture. The invariant is simple. Completed refunds plus active refund reservations never exceed the captured amount. We append refund journal entries. We do not rewrite the original capture. That keeps the financial history explainable. Merchant notifications leave through an outbox committed with the payment transition. A dispatcher signs each webhook, retries with backoff, and keeps a stable event ID. The merchant can deduplicate deliveries and replay missed events from a cursor. A dead letter path isolates endpoints that keep failing without blocking other merchants. Reads come from the authoritative payment record or a versioned projection. Every response includes the payment ID, state, version, and latest operation. The client can safely poll after a timeout and can recognize stale information. Card numbers stay outside this service, behind tokenization. Logs redact sensitive fields. Merchant boundaries control every key and query. Financial journal and audit records remain durable for 7 years. Return to order 84. The merchant creates one durable intent. Confirm creates one durable processor operation before the network call. A timeout becomes unknown, not failed. Callback and reconciliation converge on one guarded transition. Refund reservations enforce a hard cap. And the outbox makes every merchant notification replayable. If you remember one picture, remember a torn response beside a payment marked unknown, with 2 recovery arrows converging on one captured state. That is how the system turns unreliable networks into one explainable payment outcome. You can practice the complete OpenAI payment system interview problem and compare your design with the editorial on FastPrep.